I'm glad to introduce you to the webinar of today, which title is Demonstration of Close to Real-Time Cross-Border Flexibility Market. This webinar concerns the experience of real-life demonstration activities on the possibility of cross-border flexibility activation near to real-time while complying with grid limitations. The near real-time potential of flexibility of either producer was explored. New tools were developed and live demonstrated to estimate the remaining flexibility 15 minutes before delivery time. The process is implemented, resulting in a real cross-border activation. The speakers of today are Goran Ashman from ELES, Andrea Bello from HDE, Miran Kavrecic from HSE, Dusan Vlaisavljevic from EKC, Marilena Lazzaro from NG, and Charles Pemon from RTE. Please use the question and answer tool to pose the question during the webinar. The speakers will answer at the end of the presentation during a roundtable. The recording of this webinar will be available in the ISGAN YouTube channel. Now, it's time to leave the floor to the speakers, so I kindly ask to Goran to start sharing his screen.
So, hello also from my side. Thank you for kind introduction. Today's webinar will be split in 6 topics. First, a short introduction done by myself, then followed by 4 thematic parts where partners on our project will explain what they developed and what we demonstrated during the 4 years and 4 months time of the project itself. And this will be followed by a short conclusion. Within our project, we focused on close to real-time potential of flexibility. As mentioned in the beginning, this is part of a larger project called OSMOSE, where within work package 6, we focus on this particular topic. What we were investigating is, or was, how to use really short-term forecasts of renewable production, renewable energy generation, and how to see or execute additional cross-border exchanges and better utilize existing transmission infrastructure between 2 countries. In our case, these were countries of Slovenia and Italy. Of course, we had to prepare everything in a manner to be very fast doing so, and of course, to do it within the secure boundaries, respecting all safety measures as we do it in regular operations. There were 9 partners involved in this particular demonstration, coming from 3 different fields, 3 transmission system operators from Slovenia, Italy, and France, 3 generation providers, 2 from Italy and 1 from Slovenia, and 3 researchers, developers from Serbia and Italy. So just a brief explanation why our work is so interesting is it can be much better understood if we take a look how we run these processes today. And the biggest challenge today is that, yes?
Sorry to interrupt you. Could you please switch to the presenter mode? Because we don't see the full screen, the screen in full size.
Okay, and I do wear more. You don't see it in full screen. What should I choose?
Maybe, I don't know. I don't know, maybe it seems frozen, your screen. Maybe you can stop and start again sharing the screen.
Okay. How is it now?
Okay, now it's perfect. Thank you. I'm sorry to interrupt you.
Okay.
Thank you.
Oh, great to do so. So today we are running calculation of cross-border, possible cross-border exchanges on one side and flexibility market calculations as two separate processes. So we, 2 days before delivery, calculate what are possible exchanges, and then we give these limits to the market itself to be then executed either today ahead or intraday markets, or even markets that are coming closer to real time, like Marie or Picasso. But within our demonstration, we focus on how to run these things in parallel simultaneously and gain certain benefits on close to real-time calculations, forecasting, and of course, enable better or more reliable data out of these calculations, because it's based on latest data available. We based our work on a research work that was done in the past couple of years. You can see the papers that were published actually in a year before we started working on our project. So we did quite an interesting work within our demonstration, because we came that far that we were able to test our solution in real business environments. And this is network, high voltage network of Slovenian transmission system operator and high voltage network of Italian network operator, and 3 hydropower plants, 3 generation units were involved in this demonstration. So the last part of the demonstration really involved activation and deactivation of particular units and cross-border exchange of energy, while monitoring the effects of such activation on the state network state. The processes that I mentioned that run in parallel, you can see here. So on left side, it was part where we focused on optimization of production portfolio and calculation of flexibility bits. And on the other side, we prepared snapshots, so real network data and limitations, and all that came into the optimization tool that respected both sides of the processes and calculated what can be activated, deactivated, exchanged cross-border. And here you can see more in detail that this meant developing a couple of different platforms and tools. 2 particular tools were developed. 2 particular tools were developed by generation units providers. You can see here a portfolio optimization tool. And out of these 2 tools, and the other was developed by HDE, both will be presented later. And this was then sent to the flexibility bit tool, FAB, which was once one separate tool. And on the other side, network data was re-prepared by N4M platform or tool developed by EKC. And all that was then, all that data from these different tools was sent to the optimization tool developed by RTE. The final result was whether there is a safe possibility to activate or deactivate certain generation units close to real time. And activation or deactivation signals were sent through TSO SCADA system. And as mentioned, at the end, resulted in activation or execution of those bits. And now we will switch to the first topic from the to learn more about two optimization tools that were developed by HDE from Italy and HSE from Slovenia. And please, Miran and Andrea, you can start your part of presentation.
Okay, thank you, Gorazd. Welcome also from my side and side of HSE. I'm Miran, and I'll present FAB calculation in general and one calculation in particular. But let's start at the beginning. What was the idea of participant on this market? So who could participate? Basically, every flexible unit is welcome on this market, but not every can participate. We created a simple rule which tells something about the requirements for the unit to be able to participate. So for the unit to be able to participate, it has to be eligible to provide AFRR, but it should not be used in the process. This means that we need in this market units that are flexible, that are responsive, but on the other hand, we do not like to take units outside the auxiliary services market, and we would like to create new opportunities for them. So units that are reserved for capacity should not be used and are not, let's say, welcome on this market, but units that are capable of providing such services and are not used for them, they are very welcome and they can participate on our market. In this way, we do not impact on the capacity used for auxiliary services, but on the other hand, we use units that are still responsive, controllable, and can send feedback. In this way, we create new opportunities for these units that can add value for them. So, bits are calculated in three ways. One way is to be calculated from the residual and unused flexibility in existing markets, let's say in day-ahead markets, in intraday markets, where we use the flexibility to maximize the production value of the energy. The other possibility to create the bits is from flexibilities that are not used by auxiliary services. And the third option to calculate the bits is to create the bits by minimizing the potential imbalances inside the balance group. So I will present one of the possibility to create the bits. Gorazd, next slide, please. Okay. So HSE created a module which used linear optimization programming to create the bits of flexibility to be used on our pilot market from the flexibility that was not used in the currently available market. So after the closure of the regular intraday market, we believe that there is still some opportunity to gain or to extract some flexibility from our portfolio and to provide it or to put it on our near to real-time cross-border market. So one of the three calculation models was developed by HSE. This FAB, which FAB stands for Flexible Energy Bit, is created from flexibilities that are not used in the current market. And this flexibility is gained from the last minute technical optimization. So we take our currently available or currently defined commercial schedule, and then we run a technical optimization to fulfill the schedule in a technical optimal way And then if something could be still extracted from the portfolio, we calculate at which price can we do that, and we put that price on the bid, and we put the bid on the market. The limitations that we had with such calculations were basically linked to time. So the time of the calculation, we are also limited to which units can be used, or did we report everything on REMIT before we use, or we do not use certain calculation. We have to report any outages before these outages are reflected in our bids and so on. But we also see some advantages. Such advantages are to have the possibility to exploit the unused flexibility or flexibility gained from the optimization after existing markets. We believe that there is possibility in this place, and through the demonstration process, we also identified some possibility of the flexibility that could be used in these near to real-time markets. While implementing the pilot market on our side, before the testing, we realized that we would have to change and also to replicate the automatic gain control to be able to fully replicate the linear program of our portfolio. So basically, these bits are calculated without replicating the AGC, which stands for automatic gain control, but the accuracy of the model was still good enough to be used in near to real time. And the bottom line of the demonstration test were that we think that we might be fast, but to be able to participate in real time, let's say in the most future way of near to real time, like peer-to-peer trading, we are still not enough fast. We still need some simplification of the portfolio, or maybe some faster machines to calculate and model the portfolio and then calculate the bids. So this is very in brief the bidding process in general and the calculation in one of the possible way. So I will leave the floor now to Andrea. And thank you for your attention.
Thank you, Miran, very much. Thank you, Gorazd. Yes, so now from HDE side, we developed the integration of non-dispatchable renewable energy sources, which is one of the 3 calculation modules cited by Miran. So the requisite is that the provider have a portfolio management of power plants. And the idea is to use nowcasting to forecast the production of non-dispatchable renewable energy sources. Then this production is compared to the last market schedule, and in this way we can obtain in advance an estimation of the upcoming imbalances. At this point, we can balance our portfolio to avoid those imbalances. At this point, we can use those changes in the production done to avoid the imbalances. We can use these changes as FlexEnergy bids. So the imbalances generates from the non-dispatchable power plants, but thanks to nowcasting and balancing of portfolio, we can transfer those imbalances to dispatchable power plants, which can in turn produce the FEBs on the market. Yeah, so of course this approach needs to develop a custom model for each power plant, because of course those are quite case specific, and also our portfolio is required. The advantages are of course that we can reduce the imbalances and reduce also the activation of frequency regulation reserve, which is usually provided by thermal power plants. So we can also reduce the ecological impact of the power system. On the next slide, please, we can see our case studio. Please, Gorazd, thank you. This is the run-of-the-river power plant ALA. This was used as a case studio to demonstrate this concept. This is a 38 megawatt installed power plant. And so we developed the 3 nowcasting models, 2 deep learning and 1 cut boost model. And we compared the performance, which were quite good for all of 3 models. Yeah, so at the end of the demonstration, we couldn't actually demonstrate the balancing of portfolio because it is still not allowed in Italy. Anyway, this part was already demonstrated on the other calculation modules as explained by Miran. And the challenging part in this case was the nowcasting, which was actually demonstrated in a real situation. So what we learned is that, of course, the limits coming from the real time, from the real world. We had delays in real-time data acquisition, and also the fact of having near to real-time bidding, because it's clear that in this case the most advantage comes from having frequent update of the nowcasting estimations. So of course there is a need to have a frequent update of the bids, and also to exploit at its best the near to real-time feature of the market. Of course, this would require a full automatic bidding because human intervention cannot be used at this frequency. Okay, for this calculation module, I think for the given time it's all. So for the next speaker, I can give back the word.
Yes.
Thank you.
So we are moving forward to the parts of where the bids were sent, as if you remember from the previous slides, to the FAB platform, which will be explained by Marilina.
Yeah, good afternoon, everyone. It is a pleasure for me to present the work done by engineering in OSMOSE, in particular in the work package 6. Okay, engineering was responsible for the development of the FlexEnergy bid creator tool. This tool supports different calculation modules in order to create the FlexEnergy bid, and also address the overall bidding process. This tool enables each flexibility provider involved in the project to offer their flexibility that is formalized through a FlexEnergy bid on the FlexEnergy market. And also this tool allows the flexibility provider to know which is the results of the market. So if the bid that was submitted has been accepted or not. And this tool is able to support the calculation model developed by HDE, by HCE, but also integrate a calculation model able to exploit the unused FRR resources. It is developed as a web application, and the tool is online. It is able to be exploited. And from the technical point of view, it is composed by two parts: a backend that implements the overall logic for the implementation of the bidding process, and also for the creation of FAB for an unselected FRR. And the graphical user interface that is important, since also other flexibility providers using different calculation model are able in this way to upload their bids and to submit these bids to the market. Next slide, please. Okay, this is just to give you an overview of the tool. It is the graphical user interface, the front end, and I'm going to explain you the main tabs of this tool. Starting from the upload files, this tab is important since allow the creation of the FAB for unselected FRR. In order to run this calculation module, the flexibility provider has to upload some files. Some of them are provided by the Italian TSO, Terna. Some other, like the pricing strategy file, is created by the flexibility provider. For example, the VTT file contains the technical information about the production unit that can be exploited. Once the flexibility provider uploads this file, the calculation model create a suggestion, a possible selection of fab that are shown in the fab creation file. Using this tab, using this tab, the flexibility provider is able to modify this fab, for example, changing the quantity to be offered in the market or the price. And using this tab, is able to submit these bids. Even if the flexibility provider is able to create the fab in advance, these fab are in any case submitted to the market near real time. So basically 15 minutes before the optimization process will start. Using the edit fab tab, the flexibility energy provider is able to modify or in case delete the fab that was created in advance. And using the market results is able to understand if the fab was accepted or not. As you can see, there is also another tab, upload fab, that is the tab that was created in order to allow the other flexibility provider like HD and HC to upload their fab. So using this tab, they are able to integrate the calculation model they developed by on their side to the bidding platform. Next slide, please. Okay, this is again an example of the market results. So once the market results are available, the tool shows it to the flexibility provider, which is the information in this page. First of all, the fab ID, that is the identifier of the fab, the timestamps, so when the fab will be activated, the power, and the max power. So the power is the power that was accepted by the market. The max power was the maximum power that the production unit should be able to provide. And of course, also the price. Where you can find the red cross means that the bid was not accepted. So thinking of how we could provide advance on this tool, of course, an advancement, an improvement could be the integration with this tool, for example, with the Terna system, in order to avoid that each time the flexibility provider has to be download the needed file, like the VDT file or the FRR advanced file from the Terna system, and upload this file on this tool. So this is an advancement that could be done in order to allow the exploitation of the tool. So basically the integration with the Terna system, like the development of specific API. So this is okay. Engineering was also responsible for the development of another tool, that is the FlexEnergy bid pre-processing and merge tool. The main goal of this tool was to check that the fab, that is an XML5 with the schema defined inside the project, was compliant to the expectation. And when this file, so the fab XML file that was submitted with the previous tool to the flexibility provider is compliant to the schema, can be merged in a unique file that is the input of the FlexEnergy market optimization platform that was developed by RTE. This quality check is also done in order to check not only the compliance with the agreed XSD schema, but also additional control are performed, for example, verifying the consistency of some relevant information provided in the file, like the network data, or so in the specific case, the grid node ID and the grid area. We have a KPI associated to this tool, and as you can see, the results is very positive. So this means that each time that the fab was created by the flexibility provider, with a different calculation model that are available in the work package, this file is compliant to the defined schema. This is a good starting point for performing the overall process of the optimization. Okay, so that's all from my side.
Thank you.
I leave the floor to the next speaker. Okay, Casey.
Yes.
Thank you.
So in parallel to this process that was explained by HD, HSC, and engineering, the process of preparing grid models with tool N4M was running, just to better understand, and it will be now presented by Dusan.
Hello, good afternoon to everyone. So within OSMOSE work package 6, EKC was involved to develop the tool that will support the operation of FlexEnergy market platform by preparing the electricity network data for market optimization. This tool is developed as a standalone tool, which was integrated in the overall platform of the FlexEnergy market. The aim of the tool is twofold. The first one is to process the real-time data obtained from the state estimators of the SCADA systems of the involved TSOs and produce the merged regional network model that will contain the 8 power systems of Slovenia, Italy, but also the neighboring France, Switzerland, Austria, Hungary, Croatia, and Bosnia and Herzegovina, and to prepare that regional network model in real time and send it to the optimization platform, along with the second task, and that is the preparation of the list of the constraints from the network side. Those constraints are defined in form of the critical branches, meaning the lines to be monitored, in combination with critical outages or topological states that could happen in a grid, not just the snapshot state that is a current state, but also if there would be some form of the tripping and outage of some lines. So we can go on the next slide, Gorazd. So the first function is a preparation of the network model. There were 2 main challenges in preparation of the regional merged network model. The first one is the time. So we have we perform the full market optimization and sending the results each 5 minutes. So basically we have 1 to 1.5 minutes to prepare all of the necessary network data. And the second challenge is that depending on the country, there is a different form of a snapshot that is produced by state estimator. For example, in Slovenia, this is a PSSE raw format model. In Italy, it's UCT file. And to overcome this issue and provide the fast integrated regional model, we developed several submodules. First, for each day, so-called skeleton model that contains the baseline static data that are not changing. For example, the buses, the lines, the characteristics of the lines are included. And then we, in a first step, collect the data, the real-time data from state estimator. In Slovenia, each 5 minutes, and for the others, each 15 minutes. And then we extract the variables from the models, the active and reactive power injections, voltage set points, topological statuses, transformation top positions, and net positions of neighboring countries, and then in-feed those data into the baseline skeletal model, creating one consistent regional model that we can export in UCT file format, raw format, and CGMS format. And that was the first part, preparing the common integrated regional model. In the second part, since FlexEnergy market optimization required the linearized network model, we provided so-called linearized DC-ready model by running the AC load flow calculations on the common grid model extracting the power losses and adding them to the injections on the sending end of the branches, and adjusting the limiting maximum current of the branches to respect the influence of reactive power flows in the further optimization process. So we conducted this third step of the preparation of the network model to be on the safe side when we switch from the non-linear AC load flow model to DC linearized model, which is sent to the FlexEnergy market optimization platform. So we can go on the next slide. And finally, in addition to the network model, we prepared the list of constraints on the network side. As I mentioned, this is based on the pairs of critical branches and critical outages that are constraints for FlexEnergy market optimization. Since we have in the model a large number of lines and buses, so more than several thousands lines and buses, it was vital that we perform and we develop some smart algorithm that will shortlist these constraints, that only potential limiting constraints are communicated to the FlexEnergy market platform, because also the initial test during the deployment showed that for such a short period of time, the large number of constraints cannot be easily processed by the optimization platform. So we developed the smart algorithm that will decrease and only send the constraints that could be actually limiting constraints, and that other redundant constraints are excluded from the list. We performed this algorithm and shrinking of the list by having 3 steps. In the first steps, we calculated the nodal PTDFs and OTDFs that indicate how the power transfer between different nodes impact potential limiting critical branches, and using the best practices from the current European market and the flow-based calculations, apply the 5% filter. So we excluded the branches that are basically not so much impacted by potential trading on the FlexEnergy market. And also for the outage transfer distribution factor, we selected as outages only the branches that the tripping of those branches can cause significant change in flow over the critical branches that were selected. So that was done as a first step. As a second step, we deployed so-called pre-solve function, which aims to compare different CBCOs that are selected in step 1, and if the algorithm detects that 2 potential constraints are redundant, meaning that there is no possibility that, for example, constraint 2 can be activated before constraint 1 due to the impact of the potential FlexEnergy sources that are participating, that we know from the FlexEnergy bids, and potential nodal PTDFs that they produce, we can exclude some branches that could not be a limiting factor before some other branch. So basically they are redundant from mathematical point as a constraint. And this is shown here on the right. You can see this yellow surface. This is a simplified 2D picture. Basically, it's not lines, it's different planes. But on a simplified picture, you can see that lines or verticals represents the potential constraints. And if you have some far away line, you can see that that line could not border before some other closer lines, this yellow surface, which represents the space for the solution. So basically, those further away lines are excluded because from mathematical point, they have no meaning, but they will use time in processing them by optimization platforms. So we exclude them. And as a final step, we measure basically the potential of the flexibility market, what I mentioned, based on the submitted bids, and based on the real-time data that we have, how much this yellow surface can expand. So if we have, let's say, 10 power plants, we know the minimum and maximum of the power plants, the potential dispatch shift. So we check the extreme values that could happen and check whether this yellow surface could expand to some constraint in a form of critical branch and critical outage. And only if this is the case, that constraint will remain. Finally, as a result of this algorithm, we shortlist the constraints to only 30 critical branches and critical outages, thus allowing the optimization platform to perform the optimization in a really fast manner, which is expected by such flexibility markets. I must say that one of the main reasons for us to be able to decrease such level of redundant constraint is that we are close to real time. We have knowledge of a lot of data. We have a lot of certainty. So there is a possibility to have such high success in creating this shortlisted level of constraints. Finally, we provide as a result so-called crack file, which is a contingency list, remedial actions, and additional constraint file in Central South Europe format, and send that file along with the merged regional model to the brain, to call it the brain of our platform. And this is the FlexEnergy Market Optimization Platform, which I will leave Charles and a colleague from RTE to present. Thank you.
Yes, please, Charles. Dusan announced you well.
Yes, thank you, Dusan. Hi, everybody. So I'm Charles Piment and a research engineer at RTE. So we try to develop the core optimization of this tool, which is mainly based on an optimal power flow included in a model predictive control algorithm. So there on the slide, you can see the main part of the tool that we talked about earlier. So we now have all the bids. We have the network which is merged, and we have the critical branches to monitor on the outages. So now the target of the optimization is to select the right bid for the system, meaning the least cost solution, knowing their prices. So the model predictive control algorithms aims at trying to model the future states of the network. So it's what you can see on the small figure below with the green channel. And in this future, just to find the right path for each bid in the future, assessing what could happen in the network for the next 30 minutes ahead in our tool. So we try to model the future and keep the decision right now, the best decision for the bids at each time step. And then we continue to move forward like this and adapt to the uncertainties of the network. Next slide, please. Okay, so this slide is to remind how it works in real time and what we really call real time. So what you can see on the left part of the slide is the inputs, as always. So for an activation at noon, then we receive the snapshots around 10 minutes earlier at 11:50. Then we spend some time at processing the bits. It takes around two minutes. Then we process the file of the networks. It takes around 2 minutes again. Then the optimization tools takes at the maximum 2 minutes of calculations, and we are able to send the signal to the power plants through the SCADA at 12 in order to activate using the ramp of the power plants and reach full activations at noon plus 5 minutes. So what we call close to real times. It's this time frame. So we get the data between 10 and 15 minutes before the real time, and we activate at real time to get the full activation 5 minutes later. Next slide, please. This section is just to go a bit deeper inside the core of the optimization model, and to remind that it is a complex system with different parts, meaning we retrieve the data from the other partner. We mainly collect, convert, and clean those data using an open source library developed by RTL, which is called Possible, that you can use freely if you want. We then use those data which are processed and send them to the optimization core, where the problem is modeled using the ample language and solved by the Express solver. Then once we have those results, we convert those data to the SCADA of the TSO for activation to the power plants through the SCADA also of the producers. So the Python is used as a glue code in order to be able to work all those components together. Next slide, please. So this slide is the most technical slide of the presentation. So just to remind what kind of hypothesis we have taken. So the main hypothesis is the direct current approximation in the problem. So we are then able to simplify a lot the power system through this simplification. So the flow is just the difference of voltage angles between the nodes of the network divided by the reactance. And using this approximation, we can model the problem quite easily. So it's a standard optimal power flow modelizations, where we try to minimize the cost of the system, which is the objective function, knowing the cost of each bit and the volume which are offered proposed by the producers. And we also use this model for all the time step in the future. So you have an index for each time step, and also an index for each network state, which takes into account the outages that we have in the model. And then the constraints which are included in the model are basically, we are not allowed to go above the maximum power of the power unit, and we are not allowed to go above the maximum capacity of the line on the networks. And we also respect the gradients, which is the last constraint on each unit. So this is really the problem which is solved inside the optimization core. Next slide, please. So what we learned during this optimization is that we may have used another modelization called the PTDF rather than the one we use this time. But we managed to improve the time of calculation below the 2 minutes that we targeted at the beginning of the project, compared to the 4 minutes we had in the first versions. So the whole process now take less than 5 minutes, as we showed just earlier in the time frame, in the time chronicle. And the optimization tool during our test managed to reach 98% of success, and the 2% for which we had the failure were mainly due to data error. So some error in the files or in the bits, which we are not able to, then we are not able to process the optimization after. So the last slide, yes. So what we learn is the fact that the most impactful constraint and the problem is the number of CBCO, so the critical branches and critical outages that were given by the tool of EKC. So their work on the minimizing the number of those couples was very important. We should have tried also another modelization of the network based on PTGF rather than the full network modelization that we chose. So we may have saved some time using this other modelization. And the main difficulty was how to integrate this optimization tool in a real IT production environment. It was the most challenging part in the project. To go from a prototype to a pre-production tool, knowing all the constraints of a real environment. Okay, it's the main takeaway on my part.
Thank you, Charles. So let us conclude. You were able to see and hear that we ran quite a complex demonstration and complex project itself. So that's why we have to also envision or prepare ourselves to run the demonstration in 3 different steps. In the first step, we were running all the platforms individually. So platform by platform was installed in real business environment of ELES and was running there. Then step 2 was fine-tuning the platforms to work together. If you remember the earlier slides, some processes run in parallel, some processes have to provide certain data to the optimization tool in time in order to respect the time limits of the whole process. During this phase, we managed to find some bugs, some unbugs, change or adapt how we exchange data. And then the last step was running the simulation in the real business environment, finishing also with real activation of generation units. So here just a brief, more in detail explanation of what we did within the demonstration itself. 3 units from 3 different companies. The third company was Enel, also from Italy. HD and HSC presented their work, and they were submitting bids. Then during this final demonstration part that included activation of units, we were taking in snapshots that were then, as explained by Dusan, rearranged, and data was prepared to be digested by optimization tool, and optimization tool provided activation list that further resulted in sending the activation signals from transmission system operator. Actually from ELES it was sent to Slovenian HSC, and from ELES the signal was sent first to Italian transmission system operator Terna, and then further sent to 2 generation units on Italian side. Real activation then resulted in operational results that were within expected safe boundaries. So we can say that the demonstration tests were executed successfully. What were some key findings during our work? Of course, during our demonstration, we did not take into account the whole portfolio of our 3 partners, but just parts of their portfolios. So what we were able to see that this can result in a bit less possible bits that can be provided, but with more renewables in the future and more participants, this could improve significantly. Then what's important to mention is that although we prepared everything to work as a whole, these certain parts can be used separately. So optimization tools can be used also in some other processes by the generation units providers, and also the tools that were developed on the TSO side or for the purpose of processes run on the TSO side can be used separately. And this is a great advantage of our work. Of course, we could further investigate or further work on these particular topics. One focus or one direction could be to include also the DSO level of the transmission system network. That's one thing. We could be running the tool to address certain issues on a regional level. So it doesn't need to be a cross-border use of such a tools. It can be used in a certain region of a country. We could be adding additional data. So right now you were able to see that we were looking into hydropower plants. We could be adding either batteries, or we could be adding additional data on the transmission system side, like dynamic line rating data. And all these together could even improve our operation. And of course, the tools itself could be used. And we can say that at least RTE is using part of the tools for better decision making, and where they are focusing on congestion management on their side. You can find much more detailed data on OSMOSE webpage, where our deliverables are published. We mentioned here a couple of those. You can also see or read more within the paper that was published on our work, and we expect to publish at least 2 more papers this year. And I would conclude with words related to the OSMOSE project as a whole. So we are part of the OSMOSE projects, and there are 3 upcoming webinars that you are kindly invited to attend. So one next week and two weeks from this one. Please take a look. Some interesting topics will be presented there. Thank you for your attention. So we are glad to answer any additional questions. And I'm sharing here also the contact details. If you would either later or when you would be reviewing the presentation itself, come along with some questions that were left unanswered, you are of course invited also to send us an email, and we will be glad to answer you more in detail.
Thank you, Gareth, and thank you to all the speakers for sharing with us the findings of your research activity and in your project. And so, yes, as mentioned, please pose the questions. If you have any doubt or you need any clarification, use the question and answer tool so that we can have a round table and take advantage of the speakers. Maybe. I don't know. I can leave in the meanwhile. We don't have question as of now. I can ask you maybe if you have some additional remark, some consideration that comes from the project, because you developed an interesting activity, an interesting demonstration, and maybe you can highlight the challenges that you still see that need to be addressed in the near future.
I would then use the opportunity to ask questions to my colleagues to help them tell a bit more. So for Miran and Andrea, a question would be, what would help your companies to make it simpler to offer additional flexibility to the markets? That would be to you. Then to Dusan, what would you suggest on the TSO side? What could be done on TSO side to save some time that was needed for you to prepare the crack file that was sent to optimization tool? So what would you suggest to TSOs? And Charles, where do you see possibility to save some additional time on one side? And if I left anything on how this tool could be used within TSOs. So maybe first Andrea and Miran.
Okay, Goras, thank you for the question. If I understood correctly, the question was what could be useful for us to offer more flexibility on the market. And the answer is lies in our presentation, and this is more liquidity near to the real time, or in a way to extend the intraday markets. So we are observing that we can offer still some flexibility, but we are limited with the intraday gate closure times, especially for the cross-border trading. Slovenian power market by itself is relatively small, and it does not offer much liquidity. So extending this gate closure time for cross-border trading, which we tried to experiment and we tried to do in our project, to extend this gate closure more to the near real time, increases the liquidity of the market, because the market is then connected again or still connected with the neighboring markets. And the connection with the neighboring markets increases the liquidity. So this would help us not just to offer some flexibility, but also to exchange flexibility with other participants. So basically, the answer lies in our project.
Okay, thank you. So you are inviting people to take or to read our deliverables, yes?
Of course.
Yeah.
Thumbs up.
Good, good. And you, Dusan?
I think that the process could be speed up and be closer to the production, let's say, for the launching or some dry run testing before go live, is that TSOs make quality and uniform formats of the data they produce on the SCADA side, so that there is a form of uniform format that would be agreed and provided in forms of model, and that would speed up the process, because then we don't need to extract the variables and put them into the baseline model, but we would in one step just merge the models, and that would save time before running the algorithm for pre-solving and shrinking the list of constraints.
Okay, you are also involved and expert on changes that are upcoming on the mechanisms used for cross-border exchanges, you know, PTDF metrics and so on. So where does that stop, and where we are adding on with what we did within our work?
From the grid side, I see a lot of potential also to including the redispatching in such as additional services to flexibilities that's close to real time, that if we don't have the secure situation in the grid, we can use the flexibilities and this fast calculation and sending signals to in an economic efficient manner to solve some conjunction, and also combine it with let's say close to real-time market operations. So I see the potential there to making more efficient use of flexibilities. And also what you have mentioned in one of the key takeaways, also the excellent thing is the implementation of dynamic line rating, which could also enable more capacity for these short-term markets, potential flexibility market or the current intraday and balancing markets.
Thank you. And you, Charles. So what could be done, let's say, just on hardware side, processor power, computer, what time could be, how time could be shortened there? What could be done with adjusting the algorithms itself, maybe using different programming tool? But even more interested I am, where do you see the potential for this optimization tool to be used further?
Yes, on the first question, I would say that we could have tried another modelization based on PTDF or transmission distribution factor, rather than the full network modelization that we used for this experimentation. It's the first point. I think we could compare those two approaches, and we may have some gain on this part. And moreover, I think we may also take some calculation made before by the CBCO tool from EKC. For example, their work on the matrix. Maybe we could extract some information from this and use it in the optimization core rather than calculate it again. So we may gain also some time at this part. And after we didn't really try to change the hardware, we used a standard computer to make the calculation. So of course, with some maybe parallelization on HPC computer, it could be more faster probably. On the second question, how we could use it as a TSO? Yes, as Dusan said it, for example, for automatic redispatching based on cost of the units, it could be used. And in France, we use exactly the same kind of algorithms, an automatic tool regarding the limitation of renewable power in order to use all lines at the maximum of their capacity, and even linked with dynamic line rating as stated by Dusan earlier. So it makes possible to use our assets as a TSO really close to real time, as we know that some algorithms can solve the issues that we can find in real time. So it's a great deal for us to be able to use those kind of algorithms in real time in order to optimize the system and to deal with the uncertainty of the renewables power.
Great. Thank you, Charles. I see we have one question from Roberto. Are you considering TSO development plans? I'm not sure I understand the question. Do you mean long-term development plans or? Okay, I will leave it open because I don't understand. If it's related to long-term development plans, then I think it was presented quite well. That we take into what is already developed or what the real network state,